Hello everybody, I'm Leonardo Lai, and in this presentation I'm going to show you the results of our recent work to reduce the latency in the 5G stack by means of high-performance networking frameworks like DPDK. The paper is authored by me, Gabriele Ara, Tommaso Cucinotta, and Luca Valcarenghi from the Sant'Anna School of Advanced Studies in Pisa, and Koteswara Rao Kondepu from the Indian Institute of Technology. As of 2021, there are more devices connected to the internet than there are people in the world. As their number grows, interconnecting them in a fast, affordable, flexible, and scalable way represents one of the greatest engineering challenges ever. The fifth generation of mobile networks, also known as 5G, aims to support different kinds of scenarios, including high bandwidth, high density, ultra-reliable, and low-latency communication for those applications that have strict requirements in terms of reliability and quality of service. 5G brings to the table many technological innovations, and its flexibility is only possible thanks to virtualization by design. Remodeling the network functions to be realized in software instead of hardware allows to create, relocate, and scale the components when needed. Through the so-called network slicing, the mobile operators are able to create multiple independent logical networks with custom configurations on the same physical infrastructure. In the 5G architecture, one of the most discussed topics is how to apply NFV principles to the base station functions. In particular, what's the optimal way to split the radio access network functions into multiple units, namely the remote, the central, and the distributed units. The remote radio units are small distributed components near the antenna whose function is to connect the user equipment, for instance a smartphone, to the base station. The base station itself, called GNB, can be split into different physical entities, a central unit and possibly hundreds of distributed units. The optimal functional split, that is, deciding which responsibilities to assign to the CU and which to the DU, depends on the use case and the performance requirements. Sometimes it's necessary to perform some functions closer to the antenna. Other times it's more convenient to centralize the same functions in a powerful data center. Regardless of the split option, the CU and the DU need to communicate efficiently between each other in the mid-all network, and they do it through an interface which is standardized and called F1. Actually, the F1 interface comprises two sub-interfaces, the F1C for the control plane and the F1U for the data plane. In our paper, we focus mainly on the F1U interface because it's the one which transports user data and whose performance it most critically affects the quality of service delivered to the user. Please observe that the F1U interface is based on the UDP protocol. As you will see in the next slides, this detail will be pivotal for our work. Looking at the big picture, one should not forget that CU and DU functions are typically realized as virtual network functions, and in some ultra-low latency scenarios, the CU and the DU are deployed in the same location. In such a short-range communication, even the operating system can become a bottleneck and contribute to a non-negligible fraction of the overall latency. Well, in our paper, we do indeed investigate alternative approaches for the intercommunication between these two units, approaches which completely bypass the kernel networking stack. Today, there exist plenty of advanced solutions, either in hardware or software, that contribute directly or indirectly to mitigate the large overhead of network operations in virtualized and non-virtualized environments. If on the hardware side we can mention, for instance, SRIOV, on the software one we have several tools and frameworks available like DPDK, NetMap, PFRing Zero Copy, and so on. While there are of course differences in the implementation, interfaces and features, most of these frameworks share the idea of moving the data path out of the kernel and deliver the raw packets to the application level in user space. Combined with other tricks like polling, avoiding memory copies, lockless data structures, and exploiting architectural elements like the cache in a disciplined way. Frameworks like DPDK can totally bring the networking capabilities to the next level, achieving minimal latency and throughput beyond dozens, if not hundreds of gigabit per second. In this paper, we consider DPDK, which is arguably the most popular and production-ready framework in this context. DPDK, initially developed by Intel and now managed by the Linux Foundation, is an open-source project consisting of a set of libraries for efficient packet processing. DPDK is compatible with many platforms, and it enables access to network devices and their queues directly in user space through the UIO and VFIO drivers. Among the other features, the PDK supports SRIOV, multithreading, num awareness, and also allocation from memory huge pages to reduce the impact of page faults and TLB misses. The only drawback, if any, is that such frameworks usually come with a custom, non-standardized API. That is, an existing software that wants to move to the PDK to get its benefits must be necessarily rewritten in its network components to use the API of the DPDK libraries. This is perhaps a necessary evil. It's what you get for asking more low-level control for the sake of performance. On the other hand, we do believe that some high-level concepts, like sending a packet from a host to another, could be expressed through a unified API regardless of the acceleration technology that runs under the hood. So, back to our problem, we would like to accelerate the UDP-based F1 interface exploiting DPDK, but DPDK does not know what UDP is. It fundamentally stops at layer 2 of the network stack, and everything above it is left to the programmer, despite offering some utilities to implement common IP-level operations. At this point, what we did was to survey the existing open source solutions to bridge DPDK to the applications up to the UDP level. And what we found is that while many ready-to-use projects do exist, with different approaches and maturity, almost none of them seems to be flexible enough to easily port an existing application. In other words, they often force the programmer to embrace specific code patterns, declare structures and routines in a certain way, and so on. Eventually, we decided to go one step further and build our own UDP stack on top of DPDK, which we call UDPDK as a chassis of the two names. UDPDK is open source, find the link below, and its most prominent feature is a POSIX-like API. This means, in practice, that you can easily integrate it into your application to get all the benefits from DPDK without requiring structural changes to the logic of your software. UDPDK is fundamentally an additional layer over DPDK. From the latter, it takes all the fancy perks like polling, lockless queues, and packet management utilities and packs them up to build an IP UDP stack that can be accessed from the user point of view through an API that closely matches the POSIX one of Berkeley sockets, that is, conventional sockets. As we will see later, this extra layer is a great boost for portability and doesn't cripple the performance at all. You can achieve latencies down to few microseconds and high throughput. Being a transport-level framework, UDPDK supports port-based packet switching and also IP fragmentation. As you can see from the slide, the API is straightforward and it's basically the same of the standard sockets, but with a small prefix, UDPDK. You may ask, why is this prefix needed? Well, the answer is that it allows greater flexibility because you can use UDPDK sockets and standard sockets in the same application if you want to, provided that they are bound to different network interfaces. The only other minor modifications you need in your software, which are absolutely not invasive, are the function UDPDK init, which you must invoke once at the beginning, and UDPDK cleanup just before termination. Just for clarity, let me point out that a packet that is generated by UDPDK is a full-fledged valid UDP packet. On the other endpoint of the wire, you may receive it and process it with a standard network stack, and it will work. You wouldn't see any difference in the content. Let's dive a little deeper into the UDPDK architecture. We have two processes, the poller and the application one. They communicate with each other through data structures in shared memory, specifically lockless circular queues. The poller continuously polls the network interface to send and receive packets. When it receives one or more packets, it is first responsible for reconstructing the full packet in case of IP fragmentation. Then, based on the destination port of the packet, it decides which socket it should receive the data, and eventually it pushes it to the appropriate queue in memory. On the other side, the application process is where the logic of your program is implemented. When you call the receive from primitive, for example, it will pull a packet from the same queue as before. If there is no packet, then it will either block or fail depending on how you configure the socket. As for sending a packet, the routine is just specular. The application process called send-to. The packet is moved to the queue, the poller extracts it, and eventually forwards it to the NIC, possibly after fragmenting it. A descriptor for each socket is also defined in shared memory. At the DPDK level, the application process acts as a primary, while the poller one is the secondary. This design choice may seem peculiar, but it's technically necessary to ensure a correct delivery of the interrupts. So far so good. You're probably curious now to see some numbers about UDPDK performance. We connected two identical servers with a 10 gigabit point-to-point link and measured the latency and throughput with two ping-pong and packet-gen applications, respectively. The numbers turned out to be quite good, especially considering the slightly outdated hardware that we had available. For the latency, measured as round-trip time, we observed that the hosts can communicate back and forth with UDPDK sockets in less than 14 microseconds, while that would be almost tenfold higher with standard sockets. The standard deviation, which correlates with jitter, is also very smaller. The throughput, measured in gigabit per second, is strongly dependent on the packet size, but in any case it's much higher than with standard sockets. In our experiments, for a packet size of 256 bytes, it's 18 times better and nearly saturates the 10 gigabit link. And, it's important to remark this aspect, we didn't need to significantly modify the code to switch between socket types. Now that we have a performant UDP stack, let's move to 5G software. In our paper, we choose OpenAirInterface as our target implementation of the 5G RAN protocol stack. This open source project is powered by the OpenAirInterface Alliance, a non-profit consortium to develop free software for 3GPP cellular networks. The whole project is of course very large, including many components and protocols, but as mentioned before, we narrow our focus to the F1U interface. As it is implemented in OpenAirInterface, the data is first encapsulated in a protobuf, then it is delivered via UDP to the other endpoint through an asynchronous interface. In other words, there are a couple of queues both at the receiving and transmission side, and a couple of dedicated threads which are responsible for inserting and extracting messages from these queues and call the send to and receive from network primitives. This is the interesting part for our work, because ultimately we want to reduce the latency between the DU and the CU. The only remaining step is now to integrate UDPDK into OpenAirInterface. Fortunately, actually by design, this task is relatively straightforward, as it's just about replacing the calls to UDP socket primitives with the corresponding UDPDK ones. In practice, this means adding a prefix in front of each of these functions. Then we add a call to UDPDK init, another to UDPDK cleanup and interrupt, and voila, the network stack has been successfully upgraded and it's ready to use. We did it for the sockets defined in the F1U interface, that is the data plane. We left the F1C unchanged because, as already mentioned, we are not particularly interested in accelerating the control plane too. In our experiments, we measured the average round-trip time between the central unit and the distributed unit, with and without DPDK. The time measurements may or may not include a delay due to the buffer of the asynchronous interface. For completeness, we report both values. As you can see from the table, the numbers in green, which correspond to UDPDK, are substantially lower than when using traditional sockets. Perfection does not exist, and of course UDPDK has also some drawbacks and limitations. The most significant one is that polling is a CPU-intensive operation, and while it provides benefits in terms of latency and throughput, it also occupies one core, and consequently the power consumption is higher too. Also, the implementation of UDPDK is not fully complete yet, as it misses some IP-level functionalities like ARP and ICMP, so at the moment it relies on some manual configuration to cope with such vacancies. Note that it's just a matter of missing implementation. It's totally possible to support these features from a technical point of view. Similarly, not all the socket options and primitives are supported yet, and hopefully UDPDK will be extended in the future. To sum up, in this paper we have introduced UDPDK, a new programmer-friendly framework to provide high-performance networking capabilities to UDP applications. We have given benchmarks to support our claims and show that, even using the same API, UDPDK sockets can significantly outperform the standard kernel ones. Finally, we have demonstrated the validity and soundness of our proposal by integrating UDPDK into a real 5G software, reducing the latency between two components in the critical data path. In the future, we plan to extend UDPDK by adding missing functionalities like ARP, more socket primitives, and configuration options. Also, we are going to carry out more detailed experiments dealing with complex scenarios inspired by real use cases. Finally, to demonstrate the flexibility of UDPDK, we'd like to integrate it into new software applications, not necessarily in the telecommunications field. That's all, thanks for the attention. Please feel free to ask any question now or send an email to any of the authors if you need a clarification, if you have a suggestion or want to know more about our projects. Have a nice day.